Hello, I'm James Walbright, and we are Team Solar Mist. We have successfully designed a solar-powered automated center pivot irrigation system. The goals of Team Solar Mist were to allow non-arable land to be farmed where power infrastructures were not accessible, and to enhance current irrigation systems employed today. By creating a more sustainable, eco-friendly system, Team Solar Mist has not only revolutionized the farming industry, but also increased crop yields and water conservation efforts. Using some 3D printed components, the team was able to design and construct a center pivot arm to supply irrigation water to a field on a schedule and optimal cycle. We ran into multiple problems when printing and constructing the pivot. At first, we could not get the supports to print correctly. After many hours spent trying to get the printing correct, we decided to change the supports to small metal rods. We also encountered torque issues with the original motor chosen. The original motor was not able to overcome the torque of the entire pivot arm, so we had to use a larger motor. The system utilizes power during daylight hours to pump water to an elevated storage tank, thus reducing battery storage requirements. This you will hear about from Chris later. The system also uses weather sensors to optimize water requirements. Here is Mallory with more information about those sensors.
Thank you, James. I am Mallory Herrera. Our design considers rainfall, wind speed, and soil moisture to deliver a customized irrigation schedule. Through an infrared reading, the rain sensor sends a voltage pulse to an Arduino every 100th of an inch fallen. By recording the rainfall in real time, a record of total rain received by the crops can be recorded to ensure that overwatering and drowning of the crops does not occur. The soil moisture sensor takes a voltage reading across the sensor arm. Based on the output of the sensor, the volumetric water content is given, allowing conversion to inches present in the soil to be recorded. By tracking the soil moisture in real time, the system can determine whether there is enough water present to cancel an irrigation cycle. This tracking reduces the chance of root rot. The final sensor records the wind speed using a cup anemometer. The wind speed is recorded through a variable voltage output, thus allowing a system cutoff if a 15-knot wind is present, resulting in the confidence that water makes it to the crop instead of being blown away. Now here's Will with some information on the sensor data collection.
Thank you, Mallory. I'm Will Warren, and our design uses the Arduino Raspberry Pi controller. The Arduino monitors and records the outputs from the 3 sensors and converts the values to store rainfall and soil moisture in inches and wind speed in meters per second. These values are then serial printed to the Raspberry Pi, where the main program resides, and during which process the programming we encountered the most programming errors within the serial printing process, where we had trouble getting the Raspberry Pi to parse and string correctly in a form that could be read and stored. The program within the Raspberry Pi receives the Arduino readings and records them in assigned variables to be compared to the optimal values. The optimal values of rainfall, wind speed, and soil moisture are determined based on a user selection within the interface of each crop. Each crop that can be selected has a water requirement stored within the memory of the Raspberry Pi, allowing the system to know exactly how much water the crops will receive throughout the irrigation system. If the current values of rainfall and soil moisture exceed the requirement, the irrigation will cancel and recheck in 5 seconds. The wind speed is a set standard based off of USDA recommendations, and therefore a 15-knot speed is obtained or exceeded. The irrigation will cancel and be rechecked again within 5 seconds. After all sensors in the current time are checked, the resultant stop or go command is given. Now here is Chris with some information about the pumping and solar panel.
Thank you, Will. I'm Chris Rich. It was decided that we would use an elevated storage tank system to allow for reduced system costs by significantly reducing the amount of battery storage. The system pumps water into the storage tank throughout the day while the solar panels are delivering power. The elevated storage tank resides at a height of 15 feet, which provides the required head pressure to obtain the flow needed for irrigation with the center pivot arm. By utilizing this head pressure, the pump is not needed during the irrigation hours, which are likely outside of solar energy producing hours. The center pivot runs in a circular path, resulting in the corners of a field not being utilized for crop planting. As a result, the team designed the Solar Mist system to utilize the corners of the field to house the solar panels, storage tank, and battery required in order to reduce the loss of arable space. We've been contacted by 3 people on possible implementations of the system. We plan to continue improving and customizing design to suit future needs of the interested parties. For future development, we would like to incorporate cellular and Bluetooth for a phone app and like to incorporate additional forms of renewable energy. Development of the system will continue with these and other future enhancements.